Hi everyone, welcome back. Right now we're going to take a look at section 14.8, Lagrange multipliers. This is the last section we're going to cover in chapter 14. The kind of problems that we're going to try to solve in this section are problems where we want to optimize, which means either maximize or minimize some function, subject to a constraint, which is going to be another function equal to a constant. An example of one such problem we saw at the end of the last video, where we had a box without a lid, and we wanted to maximize the volume of the box, so maximize length times width times height, given that the surface area of the box had to be 12 square meters. Now, just to get the idea of how this process of using Lagrange multipliers works, I'm going to think of the case of functions of two variables. So let's suppose we have a constraint, a function of two variables equal to a constant. This is a level curve. We've talked about these before. So the constraint makes a level curve, whereas the function we're trying to maximize or minimize is variable. This makes a surface where we can then look at many level curves. Every time we set that function equal to a constant, we get a level curve. So if we look at a graphical representation of what's happening, this is one possibility. Right? So let's say this is our constraint, this red curve. This is g of xy equal to k. And each of these blue curves is a different level curve of f. And I've just given them values. I made these up. This has nothing to do with the example that we're going to eventually solve. So now if I want to maximize f such that the value also satisfies this constraint, I want to look at all the places where these level curves intersect this constraint curve. Every time I intersect this constraint curve, that means this constraint is satisfied. Now here, if I want to find the maximum value, I can see that it occurs here at x naught, y naught. This is the level curve where f of xy equals 4. This is the largest value because if I increase f anymore, it's not intersecting this g curve anymore at all. So as f increases, I'm not intersecting g anymore. And if I look at other curves that intersect g, they're smaller than when f equals 4. And this is one possibility. So this is one of the two possibilities that we're going to consider. The points where I've optimized my function subject to a constraint. At that point, the level curve of f and the constraint curve have a common tangent line. And that's what's happening in this case that I drew. Right? At this point, g equal to k and f equal to 4 have a common tangent. Now, something else that might occur, here I've drawn this f is just strictly increasing as I go up through these lines. It might be the case that f is increasing for a while, gets to a point, and then starts decreasing. So think that if it was like a sine wave or something, it's increasing, then it starts decreasing. And so I might have a maximum somewhere around here. If that's the case, then the points where I've optimized my function are not going to share a common tangent with g. But in that case, what's happening is I have a critical point of f. I have some local maximum. Again, think of like a sine curve. So it's going up, it reaches a height and comes back down. But now think of it as kind of like a sine surface. So there's a critical point there, and I know at critical points, either the gradient of my function is the zero vector or that gradient doesn't exist. So these are the two cases. And mostly for this section, we're going to focus on the first case. But the second case could also happen. So thinking about the first case, if the constraint curve and the level curve where I find my solution share a common tangent, that means that the normal vectors at this point are scalar multiples of each other. Because remember, the normal vectors are orthogonal to the tangent lines. So if they have a common tangent line, the normal vectors at this point have to be scalar multiples of each other. They're pointing the same direction, but they might be different magnitudes, different lengths. If this is the case, I can come up with this formula that the gradient of f is equal to some constant times the gradient of g. Because if I have a level curve, the normal vector is the gradient. We talked about this when we defined gradients. So in case 1, this has to be true. The gradient of f at this point where the maximum or minimum is achieved is equal to a scalar, this is the Greek letter lambda, times the gradient of g at the point where the maximum or minimum occurs. And this lambda is called a Lagrange multiplier. And that's what we're going to focus on. In the second case, let's just assume that the gradient exists, so it would be the 0 vector. Then this equation still holds. I can still use this equation where the gradient of f at the point is equal to lambda times the gradient of g. It's just now, if this is the 0 vector, I just let lambda equal 0. So in both cases, as long as the gradient exists, I can use this equation. Now this was for functions of 2 variables. If I have a function of 3 variables, I can also use this idea, but what changes? Instead of level curves, now I'm thinking about level surfaces. Instead of sharing tangent lines, they're going to share tangent planes. But the normal vectors of the tangent planes are still going to be the gradients, and the gradients are just going to get z coordinates as well as x and y coordinates. So I still use a formula where the gradient of f, the function I want to maximize or minimize, is equal to lambda, which is a scalar, times the gradient of my constraint function. Okay? So what is the method, this method of Lagrange multipliers? So let's say we want to maximize or minimize. Now I'm just going to write everything in terms of functions of 3 variables. I want to maximize or minimize some function of 3 variables subject to a constraint, which is another function of 3 variables equal to a constant. In order for this to work, we assume that f and g are differentiable, meaning that they have partial derivatives that are continuous in the area that we're looking. And we're also going to assume that the gradient of g is not the 0 vector along this surface, g of x, y, z equals k. If this was a function of 2 variables, we would assume that the gradient is not the 0 vector along the curve, gxy equals k. But really, I mean, this can extend to functions of as many variables as you want. We just lose the geometric meaning. Okay, so that's what we need. Our first step is to solve a system of equations. Here is the equation we get using the Lagrange multiplier. The gradient of f is equal to lambda times the gradient of g. And then the second equation we have is the constraint itself. That becomes part of our system. Now this looks like 2 equations, but really it's more than that, because remember the gradient is a vector. This gradient is a vector. If I have a function of 3 variables, these vectors have 3 components. This function g is a scalar function, and k is a scalar. So really what I have here is 4 equations. What do these equations look like? Well, to get an idea, I can rewrite the gradient as the vector of partial derivatives. So here are the partial derivatives of f with respect to x, y, and z. Here are the partial derivatives of g with respect to x, y, and z. That's the gradient of g. And this is being multiplied by a scalar lambda. I can distribute this lambda to each of the components and write them out as separate equations. And so this is the system of equations I'm actually going to solve. So the partial derivative of f with respect to x is equal to lambda times the partial derivative of g with respect to x. The partial derivative of f with respect to y is equal to lambda times the partial derivative of g with respect to y. Same thing for z. So I get these 3 equations. And then I still have the constraint here as my 4th equation. Now what are the unknowns of this equation? We should be able to find these partial derivatives. So those are known. But the points that satisfy both of these equations are unknown. So our unknowns are x, y, z, and lambda. So I have 4 equations and 4 unknowns. In the end, I want the points x, y, z where the maxima or minima occur. So that's really what I want to find. I don't care about the value of lambda, my Lagrange multiplier. I might actually need to find this value to solve the system at some point, but for my answer, I'm not going to care about this value. I just care about x, y, and z. So after I've solved this system, I've found x, y, and z. I might have multiple points, x, y, and z. I want to plug them back into the function I'm trying to optimize. I either want to maximize or minimize f. And then the largest value that I find is the maximum, the smallest is the minimum. If you happen to find the value of the Lagrange multiplier while you're working these out, you can just toss it away. All right, now let's actually solve the problem we had at the end of section 14.7. So here's this box that we want to optimize. We want to maximize the volume. Here's the constraint we had on the surface area. So length times width times height is my f function. 2wh plus 2lh plus lw, that's my g function. 12 is my k. So when I set up this system of equations, I need to take all the partial derivatives of f, all the partial derivatives of g. Those give me the gradient, but I'm just going to go ahead and write them as separate equations. Here's the system of equations that I want to solve. So if I take a partial derivative of f with respect to L, I get WH. A partial derivative of g with respect to L, I get 2h plus w. That gets multiplied by lambda. That's the first equation. The second equation comes from doing the same thing with taking partial derivatives to w. The third equation comes from doing the same thing with partial derivatives with respect to h. And the last equation is exactly the constraint itself. So it's exactly this equation here. And now I have to solve this system of equations. And it's a nonlinear system of equations, so things can become quite complicated. So first, I'm just going to see if there's some kind of substitution that I can do. Try to leave this up here. I'm just going to take this first equation and solve for w. Eventually, I'm going to have to use all four of these equations in some way. So if I take this first equation and solve for w, I get w equals 2 times lambda times h over h minus lambda. So I also need to assume that lambda doesn't equal h, otherwise I'm dividing by 0. If I do the same thing with the second equation, except I solve for L, I get that L also equals 2 times lambda times h over h minus lambda, so I have to assume that lambda doesn't equal h, which I've already assumed here. But w and L are exactly the same. They're both 2 times lambda times h over h minus lambda. So if I assume that lambda doesn't equal h, then w has to equal L. The width and the length are the same. So this is something I can use. Now, I've used these two equations. If I go back and look at the two equations I haven't used, I can eliminate one of the variables. Since these are exactly the same, I replace one with the other. So I'm just going to go ahead and get rid of all the L's and replace them with W's. And that sheet went away. So what's left? This is the constraint with the W's replacing the L, and this is that third equation in the gradient with the W's replacing the L's. So now I'm down to just 3 variables. I've eliminated all the L's. Let's go ahead and see if we can solve this equation for W. I could also solve this for W. You could go either way, right? These have no particular form or strict procedure you have to follow, so you end up going back and forth quite a bit. But let's just go ahead and keep solving this for this equation for W. I can combine the 2 lambda W's into 4 lambda W, subtract it to get W squared minus 4 lambda W equals 0. Then I can factor a W out, so that's W times W minus 4 lambda equals 0. So when I solve this, I know that W equals 0, or W equals 4 lambda. And I can throw this answer away. Why? Because in the context of the problem, I'm trying to find the maximum volume. If the width is 0, then the volume is 0. That's not maximizing my volume. I don't want the volume to be 0, so I throw that answer away. W has to equal 4 lambda. Now I can go back to my system of equations and get rid of all the W's. So on the one hand, I go back to this constraint, and instead of W, I'm going to plug in 4 lambda. On the other hand, so this is what I've done here, just replace W with 4 lambda, and I combine these two terms into 4WH. Now I have an equation with 2 unknowns, a lambda and h. So I need some other way of relating lambda and h together to make the final substitution and get this in terms of one variable. Well, what I can do is if we go back to the first step, where I had W equal to 2 lambda h over h minus lambda, now I have another representation for W. W also has to be equal to 4 lambda. So I can take these two things and say, okay, W is equal to both of these things, so they have to be equal to each other. And that's what I've done here. So I have this one equation, 16 lambda h plus 16 lambda squared equals 12. And now using the fact that I have 2 representations of W, they have to be equal. I have 2 lambda h over h minus lambda equals 4 lambda. And I'm going to try to solve this equation. So I can get things in terms of one variable, and I can finally get something I can solve. So I'm going to multiply both sides by h minus lambda, which is what I've done here. Now I'm going to subtract this 2 lambda h from both sides, and I end up with 2 lambda h minus 4 lambda squared equals 0. I can factor this, factor a lambda out, and I get 2 lambda times h minus 2 lambda equals 0, which gives me 2 options, either lambda equals 0 or lambda equals 1/2 h. Now, I can throw out lambda equals 0. Why? Because if lambda equals 0, then W equals 0. and we've already said that's bad. So that's what I've written here. Lambda can't be 0, so lambda equal 1/2 h, that's the solution we're going to use. I go back to this constraint. Now I know that lambda equals 1/2 h, so I plug that in. So I have 16 times 1/2 h times h, plus 16 times 1/2 h squared equals 12. I work that out, I get 8h squared plus 4h squared equals 12, so 12h squared equals 12. H has to be plus or minus 1. Now keep in mind, we're talking about the height of a box, so we want h to be positive. So therefore, we can throw away the negative 1, keep h equal to 1. So now I have h. I need to go back and figure out what the length and the width of this box is. So let me remind you that the width is equal to the length, and the width is equal to 4 lambda, and lambda is equal to 1/2 h. So using those three pieces of information, I know that L is equal to W, W is equal to 4 lambda, but lambda is equal to 1/2 h, so that means W and L are both equal to 2 times h. Since h is 1, W and L are both 2. This gives me a volume of 4 cubic meters. Now there's something else I need to check. I haven't checked out all possibilities yet, because if I look back up here, when I used this representation, I had to assume that lambda and h were not the same. So I need to check out one final possibility. What happens if lambda is equal to h? And then I can find a decision. So I consider what happens if lambda is equal to h. If lambda is equal to h, sorry to keep going back and forth. If lambda is equal to h, I'm going to look at this equation. If lambda is equal to h, I can get rid of this lambda, I can get rid of this lambda, and just put h for both of those. And so that's what I've done here. I've just replaced the two lambdas with h's. And then I can subtract wh from both sides, which tells me that 2h squared is 0, which means h is 0. Again, for the context of this problem, this isn't possible, because then the volume would be 0. So since that's not an option, I've exhausted all possibilities. The dimensions of the box have to be 2 meters by 2 meters by 1 meter, and that gives me a volume of 4 cubic meters. And a surface area of 12 square meters, because that's what we had to have. So as you can see, this idea of using Lagrange multipliers, you use that to set up your system of equations. When it comes to solving this system of equations, you might have to be a little creative. You have to go back and forth quite a bit. You need to make sure you exhaust all possibilities. Throw out answers that don't make sense in the context of your problem. So these problems can be difficult, but the difficulty doesn't really come from any of the calculus. The calculus is just used to find the gradients. The algebra shouldn't be too difficult. You just need to make sure you're not making mistakes. But really the difficulty is solving the system of equations and making sure that you haven't left out any options. So let's stop the video here. I have another example, and we'll do that in the next video, and we'll finish up chapter 14.